All right. Can you all hear me? Yes, no, maybe so. Okay, I can hear myself now. Excellent. So I know it's last day of the conference here and everyone's probably brain dead, so much information. This will hopefully be somewhat entertaining, somewhat scary, and we're going to do a ton of live demos to support this. So yeah, we're going to talk about building out an acoustical keystroke logger. And so that's basically you type on a keyboard and based purely on sound alone, like the sound of the clicking, you'll be able to determine if we can understand what letters are being typed. And so that's kind of like the idea for this talk here. So my name is David vonThenen. I'm an AI ML engineer at NetApp. I've been doing the AI thing pre-Chat GPT blowing up, so it was really kind of cool to see the thing just get crazy and wild. Prior to that, I was in the Kubernetes and CNCF ecosystem, so working on open source Kubernetes. And prior to that, I was building large-scale backup recovery solutions for VMware vSphere environments, so like cloud environments. So, like the agenda today, let's go ahead and the first thing we're going to do is talk about the moral duality of AI and ML. And the reason I kind of want to start with that is because this topic is quite sensitive, as you might guess, right? And then after we kind of talk about this moral ambiguity, we're actually going to talk about how to build one. And not only how to build one, but I did build one. And it's actually based off a research paper, but I actually made a significant improvements on top of that. So we're going to talk about the pipeline, how to build it, and we're going to all drive this using live demos. Then we're going to talk about real world attack vectors. So like how you could apply this to the real world. Hopefully you don't do this, but it's just kind of a thought exercise. And then afterwards, we'll kind of talk about how to protect yourself, like privacy and what to do about things like this out there in the wild. So let's just jump right into it. So the moral duality of AI and ML. So here's a tweet from Elon Musk, and the AI has been in the news everywhere. You can't escape it now at this point. Um, but here you have a tweet from Elon Musk saying AI is going to change everything, and it's going to be hugely net positive. So much so that it's not going to be, you know, universal basic income. He basically said it's going to be universal high income. Like everyone's going to benefit because the cost of manufacturing everything's going to drop to zero. And to me, if you just think about it for a second, we all can't drive a Ferrari or a Porsche, right? There's limits to like what you can build. So if you look at the extreme, negative outlook on it, oops. The extreme negative outlook, right, is AI is there, and here's like an MIT paper or like a thing. I think it was posted to Fortune.com where it says MIT or the MIT study says that 17 or 11.7% or about 12% of jobs in the US can already be automated. And if you look at the number of software or number of programmers in the second article here, saying it's the number of programmers in the US is at the lowest level, basically at the same level in the 1980s. They make a distinction between programmer and an engineer, but it's still a scary statistic, right? But if we just kind of like take a look at the technology itself and like what it's capable of doing, here's a NIH article, so National Institutes of Health article saying, hey, we're already using AI and applying it to cure disease, like coming up with new medications, new drugs, new applications, new surgeries, new everything. And it's making profound impact, and so kind of the idea is maybe like AI can actually help cure all disease, right? All cancers, everything. And that's really cool. It's like we definitely need some more of that. But if you kind of take a look at what AI and then machine learning can be used for, so I don't know how it is here, but in the United States, we started employing in grocery stores electronic price tags. And they're actually used to maximally extract how much you're willing to pay for your groceries. And that is really scary. So at certain times of the day, like on a Friday evening after you're done going home from work, you stop by the grocery store and you're going to pick up some groceries. They know at that time that you're there, you're going to pick up some stuff, and they digitally change the price tag so that it costs more. And that's pretty scary, right? And that's like the extreme negative of like an application of like machine learning. So why am I talking about all this? Because this stuff is all in this weird gray area. And this session is really based on this research paper, a practical deep learning based acoustic side channel attack on keyboards. So this is an archive uh, paper, research paper. So I basically use this as the foundation of this talk and like the applications and the code and everything, the models I trained, and made some vast improvements on this. And so I'm not, I'm definitely conscious of like the nature of the topic. So having said that, let's just jump right into it. So how do we build an acoustic keystroke logger? So not many people realize that this has actually been happening for some time, right? And the way you go about doing it is you take a sound, right? Any kind of sound. You typically have it, you could be an MP3, but typically it's a WAV file in linear 16 audio format. And you take that audio file, which is sound, right? It's frequency over time. And so if you take a look at this upper picture right here, that is a pictorial version of an audio file, a sound, a unique sound. And that's called a spectrographic image. So you can see along the bottom axis you have time, and then on the other axis you have frequency. And the colors and the intensity and the brightness of everything shows like how intense that frequency is at that particular time. And so using that information, if you look at the next picture right below it, you can see each one of these little cells has a different sound in them. And you can immediately see right off the bat that some of these sounds are very similar and some of them are different. But just based on like the similarity, you can see that these sounds, like the top two in the corner here, right, are probably the same sound. And that's kind of like how ML audio classification works. And there's been many examples of this happening out there. So like the basic examples you probably see are like a cat and dog. So like a cat meowing and a dog barking. But there's actually some real world applications of like hearing gunshots in urban settings, so to alert the police that a gunshot has been fired and to send them to that particular location. But it needs to be able to distinguish that gunshot from a car backfiring. And that's kind of like what we're talking about here. And some other applications, I actually gave a talk last year in Amsterdam using audio classification to detect sarcasm. So I ended up building a multimodal model using facial expression, so facial affect and like how things move around and stuff, like on your face, like eyebrows raising and stuff, and also the intonation of your voice to detect a sarcasm. So that was recorded. So the video's right there. If you're interested, you can go ahead and watch it later. We're not going to do that right now. So let's go ahead and start building it. And like with any AI or ML problem, it always starts with a data set. So we're going to use two different data sets in this talk here. So the first one is the top one, keystroke noiseless final. This was actually used as a part of a hackathon in Singapore. And believe it or not, it's basically the same problem. Take a single keyboard and determine whether or not we can actually, by the push of a button and the acoustics that it makes when you push that button, can we classify that that was the letter A or Z or the space bar? And the second data set, which is the one right below it, is a multi-keyboard acoustical data set. So this is multiple keyboards. So like Lenovo and HP keyboard, can we be able to detect what letter it is using multiple keyboards? So we kind of already described how we're going to go ahead and tackle the problem. And that's basically take an audio file, a WAV file, convert it to this pictorial representation, and we're going to collect sounds, like multiple instances for every key on every keyboard. And we're going to basically click the button, have it listen, and we're going to basically capture like 20, 30 instances of each sound for every letter on the keyboard. And then we need to assign, and since we're building a classifier, we need to like assign structure to this, right? So we put all like sounds, like all the A keys sounds, all the B key sounds in folders A, B, C, and so on. And so the labels for our samples data set is like A through Z, 0 through 1, spacebar, and enter. And so we're going to actually use 38 different keys to detect and do this acoustical classification. And like what the picture captures, time or frequency over time, RGB, 3 channels, right? We need the color to associate the intensity of frequency for what frequency at that particular time. And then we're also going to do a bunch of other things like machine learning, data scientists, things like to normalize stuff, right? Because you might not hit the key at the beginning of the recording, so we need to shift things around. We're going to make sure that all the sounds are the same time length so that we can make comparisons to one another. And that's basically what the data set processing looks like. So um, how we then take that data set, we are going to do model training, and we're going to use a CoatesNet style architecture. And kind of like, I don't want to dive into this because it, my head hurts at this point too, is you have like, the ideas is you have like local patterns, so like local frequency patterns over kind of this global context of the overall audio file. And there's a bunch of stuff that's, loss function and entropy and optimization. But kind of the idea is what machine learning is really good at is like observing patterns. And that's basically what we're doing. We're feeding the idea of just machine learning and AI in general is just feed it enough data and hopefully that it's going to able to detect in all of the key presses for the letter A, subtle, very, very subtle nuances for like what makes this the letter A, this particular sound. And that's kind of like just the idea at a very, very high level, like what this problem and what the model we're actually going to build to do this. So for that first data set, right, remember it was a single keyboard. And we're going to have multiple sounds for every, right, A through Z, 0 through 9, space and enter, but we're only going to use a single keyboard. So, that data set is multiple key presses for A, and we need to take all of the data and divide it. And this is typically done for every AI and ML problem. You need to have training data, which is like the large majority of it, which is like roughly 80%, depends on the problem. In this case, it's 80%. You need some validation data, so like 10% of it. What the validation data does is it helps hone the model so that it can more accurately predict like what key press or key sound that is. And then you have test data, which is another 10% of the data set, which is used to basically verify the model. Say, hey, now that the model's trained, I'm going to take this test data and run it through all of the different key presses to see what percentage of accuracy that this model has. So that's kind of like how model training works at a very high level. So instead of like just talking about it, I think we should just go ahead and do it. So for the data preparation, and by the way, you don't need to copy the slides down or the code or any of this stuff. Like it's actually right now on my GitHub repo, so it's all there. So everything to do this, to train the model, to run it for inference and all that is all available on my GitHub. So the first step we need to do is we need to take all that audio data. And if we go ahead and do an ls, you can see data, right? We have like the test, training, and validation data. And I'm just going to pick one training data and then the letter A. And you can see all the wave files right here. So here's for the letter A for just the training data itself. So we need to convert these wave files into images. And so to do that, I have created, I created a script in the folder at the root of this folder here. I can't ever remember the command to run to make this do exactly what I want to do, plus it would be a lot to type out. But we actually just need to run this particular script with these types of parameters, and it will convert the, right, we don't have an images folder. It'll actually convert the data, our WAV files, into images. And I obviously reduced this subset so it's only the letter A because this would take far too much time to do. So if we actually now see that there's an images folder, we can actually go into like the training data, right? There's only a single letter A, but now we have a bunch of images that represent sound. And if we go ahead and want to take a look at one of these, this is like what the letter A looks like in pictographic form, right? Spectrographic form. So this is what the particular sound for this instance of this key press for the letter A. So now that we have our all of our data, our training, validation, and test data, we need to go ahead and we need to train the model. And to train the model, you would just go Python 1_train. And I'm not going to do that here. It's going to require an H200 and it'll be about 14 hours. We just don't have that kind of time. But, and if you don't want to burn your own money, I've provided the models, which are right here, as a downloadable on my GitHub repo. And so we're going to use a single keyboard and we're going to pass in the letter S just as an example, right? Instance 9 for the sound S. And we're going to pass that into our model for inference. Now, what's really interesting, single keyboard, is that we can predict that this is the letter S 100% of the time. Now, that's pretty frightening and pretty powerful, right? But it's also like a smaller problem because it's a single keyboard. So I still think it's pretty amazing that it can distinguish all of these different sounds, right? Holding a microphone up to a keyboard, push the button, and then say, oh, that's obviously the letter S. I'm 100% sure. And that's pretty cool and pretty amazing. But let's go ahead and jump back to the slides here. That's a single keyboard. Now, what about multiple keyboards? And for our multiple keyboard data set, we have keyboards from Lenovo, HP, MSI, Apple, and obviously Zoom is not a keyboard, and neither is Messenger. But one of the keys for the keyboard was recorded over Zoom and over Messenger. So that might scare a lot of you to realize that you probably shouldn't have your microphone unmuted while typing. So that's what the data set looks like for our multiple keyboard data set. And just like before, right, we want to create a dependent data set. So we want to isolate just these 6 keyboard sounds. We are going to group them into test, validation, and training data. And same kind of distribution, 80% training, 10% validation, 10% test, and we're going to divide everything out. And again, instead of like just talking about it, let's go ahead and do that. So we'll jump into our multiple keyboard. And we'll also talk about the other, by the way, the improvements that I made on top of all this stuff, which is, yeah, kind of interesting. So just like before, we have our data divided to, right, test, train, validation. And if we look at the training data just alone, you can see now all the different keys and that we have sounds for, which have already been converted from WAV to PNG files, so images. So if I go ahead and take a look at one of them, you can see like the HP, there's like that many, 4 instances for the HP keyboard, Lenovo, Messenger, MSI, and so on. So if you wanted to train this model, you would go Python 1_train. Again, it would take roughly, I think it was 16 hours on an H100 or an H200. Don't have the time for that. So we're just going to run inference, which is, let's clear this out. We're just going to run inference and we're going to actually, we picked one random key, is this Lenovo 5. So the Lenovo keyboard, the letter H, the 5th instance of that particular sound. And we're going to run inference on that, take that image, run it through our model and see what happens. See what it can guess at what that letter is based on the sound. So you can see, so for that particular key, the letter H, it is the most confident answer is the letter H, which is correct, at 48%. And then you can see the letter G, which is right next to it, at 24%, letter J, 16%, and so on. I did top K equals 5 for a reason, which is what we'll come back to in a little bit. But kind of the interesting thing here is that it can actually predict using over multiple keyboards that particular sound, the letter H. So what's interesting is that, right, we have the ability now using multiple keyboards be able to understand that it's this keyboard for the letter H. And I kind of realized that the model isn't always 100% perfect, right? It's actually only 48%. And if you were to run enough of the letters through, you'd actually find the most confident answer isn't the first one. So that's to say that it thinks that the letter H or the letter C or whatever isn't the first one, but it might be the second or the third one. And kind of like to demonstrate this, I'm going to take a number of letters. So we're going to go ahead and jump into this folder here. So I took a number of letters, and what we're going to do is we're going to simulate me typing, right? We're going to take the sounds, which are represented by the pictures here. You can see the letters, right? A, C, D, E, G, whatever. And we're going to spell out a message. And we're going to basically pass each one of these images one at a time through our model to spell out this message. So let's go ahead and give that a try. And actually, let's go ahead and take a look at it. Oh, of course, it's verifying. Oh, there we go. Oh, wow, I did an update of VS Code right here. All right. So the message we're going to spell out is hello Greece, right? Let's see, Hello spacebar Greece, right? So let's go ahead and run inference on it. So I selected top K equals 2, and I did it for a very specific reason. So you can see the message right on the right-hand side or left-hand side here, right? Hello Greece. And if we take a look at the probabilities of the sound to see if we can determine what it is, you can see that the first word, at least, hello, is spelled correctly, Hello. And then space, and then this represents top K equals 1, like I got it in the first shot. And this is the second guess, right? So then for the next word, Greece, Greebe, which is actually mostly the way there, but it's not exactly 100% correct, right? We can actually see the C right over here. It was the second guess for this particular sound. Now, what it had occurred to me, and like what that research paper kind of like forgot to realize was that, machine learning is all probability based, and sometimes it's not the first guess. And so the improvement is we have the actual message here. We just need to jumble the letters around in order to determine what the full message is. And so what we're going to do is we're going to basically take the words and pass them through a spell checker. This sounds super obvious, right? To do this in an automated way, so I don't need to intervene, right? But we also know that if we take all of the characters and pass them through a spell checker and do all of the different combinations, that's not going to work out well because there are, I think, 12 keys here in this one. So if we did 12 keys, 2 to the power 12, we would be here for eternity trying to figure this out, right? So how can we reduce the problem so that it's much easier to do? So there's actually one key on the keyboard that is very unique. And what I mean by unique, it's very unique because it's a different size. And because it's a different size, it has a very different acoustical signature from all the other ones. Anyone want to take a guess what that key is? Spacebar. Excellent. So instead of doing everything, we'll use the spacebar to delimit the words. And that's how we're going to break it up so that we've reduced the problem and the number of combinations we need to run to, for the first word, which happens to be spelled correctly anyways, instead of trying to figure out the entire message 2 to the 13th power or whatever, now it's only 2 to the 5th power. And we can do this quite easily now. And so that's what we're going to do. Now the internet is a little slow here, but we'll get to it and we'll actually see it get halfway through. But we're going to take this and we're going to run the different combinations using the space sound, the space bar, the space key sound as a delimiter. And we're going to do the first 5 letters and run it through 32 different combinations. And as we're going and we're doing all this, we're going to spell check every combination of every word. And we're going to, and when we hit the right word where it's actually spelled exactly correctly, which we see right here, hello, we're going to just dump it to the screen right here. And for every other combination, we're just going to go ahead and run spell check, save it to a CSV file in case we want to look at it later on. And so we're going to do that for the first word. And then for the second word, and we'll actually print out in a second here, hopefully this is work. This is actually going over the internet and doing spell check against a free service. And so then we're going to use the space bar to delimit the next word, which is 6 characters in length. So it'll be 64 different combinations. And so you can actually see right here, 6 combination or 6 letters long, 46 combinations. We've already hit the spell check on it. So, and then you can see right here, here are the different probabilities for the different combinations that I've used for spell check. And the top one obviously is hello because it was spelled correctly. And um, we could even make another improvement on top of this, right? We know that the first word was 5 characters in length, but when you get words like this or help, right? We know that that's 4 letters in length, which doesn't match the 5 that we're expecting, so we can like just discard them and junk them in our analysis, right? But you can already see, and this one, by the way, takes a little bit of time because it's, and I'm just gonna move on, but you can actually see hello and then Greece, right? Which is our message here. And if we just do a cat of the right complete words, hello Greece. So we actually are able to figure out what our messages are just based on acoustic signature of typing alone. So if we were trying to do this in the real world, we are never perfect. Like even machine learning is probability based, just probabilities alone, we're going to screw up at least once. So if we wanted to do this in an automated fashion, how would we go about doing this? Where if we did get a word that was, we have no idea what the word is, we ran it through the spell checker, we couldn't figure out what it is. We don't want to go ahead, although if it was important enough document, maybe we do want to like whatever it is we're listening to. If we wanted to try to do this, we could look at it and see the different combinations and say, okay, it's this word. But let's say just for hypothetical reasons that we aren't able to figure out what that word is. So it had occurred to me to build an AI model to predict what that word might be. And I know that this is a big game in the United States like 30 years ago. That shows you how old I am. But if there's a game called Mad Libs, and it was like it's a kids game, right, where you basically had sentences that had gaps in them. And the idea was that you would pick a word. It basically said, ask your friend for a noun. They would pick a noun that was like very, very funny because they actually don't know what the sentence is. And they'd say, pick an adjective. And, at the end, you'd have this, really funny sentence because the sentence was made with picking nouns and adjectives, not knowing what the actual sentence is, and everyone has a laugh. So that's kind of the idea of this masked language model, except for instead of picking a funny word, we're going to pick the most probable word. And that's kind of like what we're going to do right here. So this also, to build this one takes actually much longer. I think it took a full day. But if you wanted to run the data preparation, the distillation training loop, you can go ahead and build this model, or you can download the one that I've already provided. But we're just going to go ahead and run inference on it just to show you a couple examples like what this actually does. So we have a couple sentences, just some example demo sentences, right? So like this sentence, right? The capital of France is blank, right? And if we run this through our this sentence with this blank spot through our masked language model, we can actually figure out that the capital is Paris. And this is like what the model provides us. The top k equals 5. This is the most probable. Paris is the capital. We know that, right? Then the next sentence as an example, distilled models are the blank of large models. Pass the sentence through our model with our blank spot, and get the top 5 equals k. Most probable is smallest, which is correct. So if you were to try to do this and try to, correct the errors as they are happening with minimal human intervention, you could use something like this to help predict things that got messed up along the way. And maybe this is recorded. If not, the demo for all of this stuff, you can click the YouTube links here and there. You can view them at home. So let's do a recap. So the results from our single keyboard and our multi-keyboard. So for our single keyboard, the accuracy was 100%, which is crazy. It's wild, right? It's like blows my mind. And the multiple keyboards, I took all of the test data, I ran it through our model. It was able to guess as like the most like what is your best guess at like what this sound is. It was actually accurate to 46% of the time. Now in machine learning and AI, 46% is actually horrible. Like it's kind of basically depending on like what you're classifying, right? It's 50-50, right? That's not a good thing. But in this case, it actually turns out to be a great thing. And the reason why is because if you were actually to randomly guess what a key on that keyboard is, the probability of you guessing it right is 3%. And so 46% compared to 3% is pretty wild for a difference. And then if you were to now consider, don't just give me your first guess, give me your second or your third guess. Now you can start to see how this problem becomes solvable. And you can run the different permutations and then use AI to fill in the blanks when it really did screw up because it couldn't figure it out. And yeah, that's kind of like the results from both of these, right? Now, one thing I did not test is now this is maybe you're like, whew. One thing I did not test was independent key data sets. So this is learn sounds for a collection of keyboards, but introduce a new keyboard to test. So like the model has never seen this keyboard. Now this accuracy drops off like a cliff. And if I had to guess, it would basically get to the 3%. It wouldn't be able to do it. But I think what it could maybe do, and I didn't have a data set to do this with, what happens if you were to get two keyboards from the same manufacturing lot? Maybe the manufacturing similarity is so identical that if you were to click a button, it might be able to detect that particular sound. And you might be like, what the heck? Here on the right hand side here is the frequency or the probability just in everyday typing. Obviously, this is language dependent. I'm using English, but it holds true for other languages as well. Like this is the probability of the letter you press over time. And like in English, the letter E is used most frequently. And so basically what I'm saying is the wear and tear by pushing keyboards where the E is pressed 12% of the time when you're typing, that will basically start to wear on the keyboard so that it'll generate that unique sound. And if it's a keyboard from the same lot for manufacturing, it probably might be able to work. So other improvements you can do, right? Some people are more heavy-handed when they type. Other people maybe not so much. So you'd probably have to collect data to, account for that variability. When you type, there's like kind of a natural flow to how you type. Maybe if you added in awareness of what was pressed before to predict the next one because the flow is a little bit different. Um, Maybe that might improve some things. Maybe doing multiple users. I don't use home row, so you're supposed to position your hands over. I actually float and peck at the keys because I just remembered where the keys are because I'm weird like that. So yeah, all different things you can possibly do to improve the model here. So real world attack vectors, really quick. This isn't new. This is, if anyone's aware of this, in the 80s, 90s, and probably early 2000s, our dial tones for payphones were all acoustic based. And there used to be a toy in a cereal box that when you blow into the toy at a payphone, it would actually give you free calls. And this was the toy that was used. So this isn't a new kind of attack. But if I were to figure out a way of like using a single keyboard attack for a keyboard that we all use very frequently, my first thought was this. And I'll tell you what the scary way to attack this would be. You know what, like a credit card skimmer, right? You put it over the face of the credit card. You put in your card. Now I have the magnetic signature on your key or your card. Use that as also the triggering mechanism for a microphone, right? Basically, to get the machine learning training data, I go up to my ATM every day. I frequent the bank anyways. That's my bank. Hit one, record the sound. One, record the sound. One, record this. Two, 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 and create a data set to figure this out. Don't do this at home. Now, for multiple keyboards, like all of us have probably our keyboards lying around. And that's kind of scary. And if you were actually able to do this just using a microphone and keyboards, you could probably figure out what you're typing, whether it's a Word document, passwords, or whatever. So now that I've scared everyone to death, how do you protect yourself against this kind of stuff? This is obvious, two-factor authentication, right? I use a YubiKey. I actually have 3 of them for different things. Um, use a YubiKey, right? If they even have my password, you still need the physical key to plug in to like decrypt my password file, right? Don't use SMS. There are actually ways to figure out and spoof and read text messages. So don't do that. If that's the only option, then do it. It's better than nothing. Use passwords you don't know. I wouldn't use a password provider on the internet. Like everything in the world, everything gets hacked. Your passwords, if they're up there, will eventually make its way into someone's hands. I guarantee it. So I use like an offline one, so something that's not connected to the internet. But it's better you don't know what password it is for your bank, because then they can't socially engineer your password based on your birthday, your kids' names, your favorite sports teams, whatever. Use different passwords for every platform. You don't want to accidentally, like, you know, one bank gets compromised, now you've compromised all of them because you've all used the same password. Change your password frequently. I know that sucks, but it's the reason why a lot of our companies make us do this. And then be intentionally difficult, right? Like you see in spy movies, you have they're talking about something that's supposed to be in secret. They turn on like the water. That's introducing noise to like make sure to add interference, right? So this all sounds super tinfoil hat and crazy, right? But I saw this article. This was a few months ago, like middle of 20, towards the tail end of 2025. Apple acquires this startup QAI, using a wearable to interpret facial skin micro movements, and that sounds really cool. And I'm sure it's very fascinating. But when I saw that, this is the first thing I thought of too, is like lip reading without any sound, just basically having a video pointed at you, a telescopic lens, listen to what you're saying without actually even hearing it, right? Using just the movement of your mouth. So like, why am I telling you all this? And why am I giving you code to do all this? Kind of the idea is that in order to protect ourselves, you need to have the ability to reproduce it so that you can kind of defend against it. So I encourage you to take a look, play with it, figure out different ways of disrupting it. And the resources, like I said, are all available on my GitHub here, including the slides, so that you can click all of the links and read all this stuff. But they're on my GitHub right there. If you're interested, there's a bunch of, like I said, the other talk that I did to do sarcasm detection using audio and facial movement. I did at AI Dev EU, which was last year, called Sarcastically Speaking. The other video here, which I think might be very interesting for everyone here, we are at We Are Developers last year. I had the session called Confuse, Obfuscate, and Disrupt. It was basically using techniques to have AI do things that it wasn't supposed to do. So this is like, think about like, jailbreaking or getting around the what is it, the safeguard or the guardrails, which are complete garbage anyways. I hope you guys realize that. But this will actually help you get around that stuff and hopefully maybe get you a discount when all these AI bots start being used on retail sites. Having said that, thank you.